Note that this video is meant to be more of an open-ended discussion or shower thought and will contain inaccuracies to the actual science behind hitting things. The video is more meant to be highlighting the complications that arise when thinking about hitting stuff rather than actually explaining anything. Okay, so hitting things is usually pretty intuitive. I swing my arm and the thing in front of me gets hurt. But like with most things in life, when you add physics, things get fairly complicated. Yes, hitting technically involves more things like biomechanics and physiology, but physics should be complicated enough for this video. But first, a crash course for those of you that didn't take high school physics. If somebody shot you with a gun, assuming they didn't miss, it would probably hurt. And there's also the small chance that you'd die, which would also probably hurt. I've tried asking, but nobody's responded so far, so who knows. So you might conclude that fast things hit hard. But most people would rather get hit by a baseball thrown by some all-star pitcher rather than some automobile going at the same speed. Well, unless you're trying to extort your university for free tuition or something. Because getting hit by a car is kind of like getting hit by tens of thousands of baseballs at the same time. So we'd need to consider an object's mass-weighted velocity, which we usually call an object's momentum. Since cars hurt more than baseballs, you might conclude that big momentum equals hitting hard. But if we consider a car with arbitrary mass and speed, and a train 100 times the mass but equal momentum, the train would be moving 100 times slower. So while getting hit by a car going at insert speed might hurt, getting pushed by a train going at 100th of that speed would only just nudge you. Because instead of going from 0 to 100, you're only going from 0 to 1. So in other words, we would need to consider how fast the thing being hit changes speed or its acceleration. But for simplicity, since mass is usually constant, we can also just consider the force. Now according to physics, we have 4 fundamental forces. Using proof by flat earth theory said so, we can ignore gravity because it doesn't exist. And we can ignore the nuclear force because the president has the launch codes, meaning only they can use nuclear force. So we're just left with the electromagnetic force. Now you might think that we could ignore this too, since humans are generally neutrally charged, but zoom in enough, but not too enough because quantum mechanics is a thing, and you'd see a bunch of positive charges slightly offset from negative charges. Meaning we could technically use an octo pole expansion with Legendre polynomials to approximate the force between two colliding objects. Of course, if you're smarter than me, you'd immediately realize that this is pointless because the act of hitting requires contact, which requires things getting close together, meaning a multipole expansion falls apart. Okay, I'm gonna be real, that was just an excuse to say Legendre polynomials because it sounds fancy. But regardless of the modeling method you use, you'd probably end up with some second order coupled nonlinear differential equation, which if you don't speak physics translates to we're fucked. Luckily, if you don't care about solving equations and just want to understand what it means, it's not too hard to figure out. Force gets big when two things get close, so we want to hit something by moving really fast to close the distance between the two things. To demonstrate, I ripped out a couple of magnets from an old headset and rubber banded one of them to a water bottle. If I slowly move the magnets together, they react fairly slowly, as you can see by the slow movements of the water bottle. But if I push them together quickly, the water bottle moves very erratically. Now you can obviously demonstrate this much more clearly with magnets on cars on a rail, but this channel is much too low effort for that. Anyways, aside from speed, we want to give the object some resistance to change in its motion, or inertia, or mass, so that it maintains its high speed and doesn't immediately bounce off the target. Or in other words, we can basically ignore most of my crash course because we basically ended up back at fast thing hit hard. But at least now we know that we didn't know why we knew. But putting the complicated stuff aside, we can probably assume that most people are going to be hitting with mass and velocity combinations somewhere in between train moving slower than a snail and air molecule moving at Mach speed. Or in other words, a magical range in which increasing momentum does increase hurt from hitting. Which is the reason why people usually opt to fight with weapons over being barehanded. If we make the completely baseless assumption that people hit with a constant force no matter how much mass they're carrying, then the actual energy in the colliding object doesn't actually change, assuming you hit the same thing in both scenarios. Because work is defined as force times distance, and neither of those factors change. The thing that does change is the momentum. If we hit with triple the mass, the velocity only increases by a factor of √3, meaning momentum increases by a factor of root 3. And similar math applies to rotational mechanics or swung weapons like bats and swords. On a side note, this kinda suggests that humans aren't really optimized for fighting since external tools are required to hit hard. Which is weird because everyone's ready to scrap on the internet, which makes humans seem like a species designed to fight. Now, to be fair, this is also because metal weapons hit a lot harder than a combination of flesh and bone. That's because I've been ignoring material stiffness up until now. Stiffness basically describes how spring-like a material is. The higher the stiffness, the less spring-like, and vice versa for lower, so I guess anti-spring-like? Anyways, instead of two rigid bodies colliding, you could also imagine a collision as two electrically charged insulated nonlinear springs colliding with each other, which is probably enough to give the average physics undergrad nightmares. But there are at least a few concepts that we can try to make sense of. For example, springs solve collisions. When a spring makes contact, parts of it are still free to move and compress, and the springier a spring is, the more it can compress. This compression takes time, meaning you could stop a springy object with less average force than a stiff object. Which is why kids can throw red rubbery balls at each other during gym class dodgeball and only walk away with a slight nosebleed. But throwing dumbbells at people isn't very safe, so I guess it's a good thing we don't have dodge dumbbell. But this doesn't explain why don't run. Pressing your shoulder into a wall hurts less than pressing up against a flat side of a nail. You press up against them pushing with the same amount of force, but one hurts more than the other. But if you think about it, less of your body is touching the nail than it is touching the wall, meaning each individual chunk of you is responsible for supporting more of the force. Or in other words, a bigger force is applied on a smaller section of you. Of course, most people just refer to this as pressure, which more specifically leads to a higher internal stress. And since structures fail under high stress, we can assume this is responsible for hurt. Which also explains the idea behind swords and guns. By concentrating a quick-moving, non-negligible mass onto a small point, you can make big hurt. And on a quick side note, you could still imagine collisions as two electrically charged insulated nonlinear springs colliding into each other, but if you zoom in enough, the springs are actually truss bridges, where trusses are made up of more springs. Which is just an extremely convoluted way of imagining a type of FEM or finite element method analysis. But back on the topic of swords, this still doesn't explain why the Japanese use thick sturdy katanas while the Europeans use thin flimsy swords. As we've discussed previously, a smaller contact surface means more stress means more hurt, right? So were the Japanese just stupid or something? Not quite, because a cut is still a cut. Both weapons cut through humans and will likely be perceived as painful, so a katana doesn't have to be super thin to get the job done. Katanas also have a hardened edge, which we've already discussed material stiffness, but hardness also preserves the cutting edge, which lets you cut through more things without maintenance. Meanwhile, European swords are a lot flimsier, meaning they require more effort to cut through things, because energy will be lost to both the elastic deformation of the blade and the vibrations experienced while cutting. And also, thin blades are more prone to chipping, which could reduce the effectiveness of the cutting edge. So were the Europeans just stupid or something? Not quite. Because armor exists. One of the benefits of armor is that it's not alive, and therefore feels no pain, meaning the high stress concentration at the collision site is basically pointless. And on the other end of the armor, where the armor actually touches people, the stress would become diluted to the point where hitting someone in a suit of armor with a katana is virtually indistinguishable from hitting them with a long sword. You're basically just hitting them with a metal bat at that point. But because European swords were designed to be flimsy, you could hit metal armor multiple times and still have a sword. But on the other hand, hardening metals typically makes them more brittle, meaning you wouldn't necessarily have a katana after hitting metal armor. Okay, so why didn't the Japanese just wear good armor? Were they just stupid? It was, and still probably is, hard to get good iron in Japan, meaning it would be hard to deck out a guy in full iron armor. And logistically speaking, it makes a lot more sense to fuel 13 people with swords and minimal light armor than it does to send out one fully decked out guy with 12 unarmed peasants. Okay, wait, I thought we were just talking about collisions. How'd we get here?